Welcome to day 2 of the asset training. So I'm Aaron Huyen, a student in the ASRL lab at University of Alabama. We've got the PI of asset, Professor Sood, with us here today. And online, we have the lead dev, James Pezent, is online also. So asset was his dissertation. He is by default the expert on it, and we'll be able to help field questions today as well. So we're going to go over actually, before I dive back into that, I'd like to thank again the flight mechanics tech discipline team and Heather and her team for sponsoring this training and making sure that we can get asset in the hands of mission designers and trajectory folks so that we can have access to this open source tool. So this will again be a collaborative open work training. So we're going to have practices again, and please feel free to speak up, ask questions, and share your code if you're having issues. We want to be able to give you practical examples that you're coding up today so that you feel comfortable to go tackle more mission specific problems with asset from this training on. And of course, it's being recorded, so this training, along with all of its material, will be posted for you to be able to go back on or share with anyone else that you want to point towards asset. So with that, we'll get started on day 2. If you recall, if you were in attendance yesterday, get my slides working again. If you recall from yesterday in day 1, we made it through the first 3 sections out of the 5 sections of this training. So the first section was going over the basic building blocks using these asset vector functions, getting used to what they are, understanding that they're not a data storage unit, they're an operator that we can and combine together with more and more complex operations to form a problem. We went over then forming an ODE within asset and having an actual ordinary differential equation solution space modeled using those ODE args, if you recall. And the reason why we did that once we have an instantiated ODE asset object, that ODE object is an interface to 2 very major parts of asset: integrators, which we went over in depth yesterday, and phases, which we introduced yesterday. So a reminder, integrators are solving the initial value problem. They're propagators, and we could do things like add stop codes for event detection. We could add control laws if our solution space was a controlled problem. But then we also introduced phases, which is how we interface with assets optimal control library and are able to form optimization problems and utilize this SciOpt custom written optimizer that leverages these analytical derivatives that we've gone to lengths in yesterday's sessions to get set up and let asset derive. So to start, we got a question?
I know you're going to some of it. Mm-hmm. Can you go over some of that stochasticity or the randomness that you were talking about, so that there's the expectation that some of this stuff is actually stochastic?
Yeah, that's a good point.
Just as an overview.
Yeah,
make it clear so that other folks, when they see it, if they see something like this, it's not surprising.
Yeah, that's a good point. So we'll hit that. I think slide 19 is where we do the optimize calls, and we'll address that there. Good, very good point. So I know we made it through the phases slides yesterday of this phase structure, but these are a very, very important structure within asset if you want to use this for optimizing problems. So we're going to go through just a quick rehash of this slide and then move on to the optimal control problems, because optimal control problems are just a way of patching multiple phases together. So it's really important to be comfortable with what these phases are and how they're operating. So I know it's a slightly more technically dense section, and I'm not going to go through in as depth as we did yesterday. So definitely keep yesterday's recording and slides on hand if you'd like to do more of a fine-tooth comb through it. But we're going to rehash these real quick, and then move on to solving complex multi-phase problems today. So just a recap of phases and a reminder, hopefully everybody's coffee is in their system now. So in Asset, a phase is how we interface with the optimal control library to solve boundary value problems. Integrators solve initial value problems and just propagate. A phase is how you actually take some solution space, so take your ODE and instantiate a phase, which is our way of transcribing that solution space and then applying any relevant constraints and objective functions to your problem that you're trying to solve. Good question. So in the for right now, in yesterday's Teams meeting, it should have saved off a recording of the day. But once this training concludes, we'll work with Heather and the flight mechanics tech discipline team to get a permanent home to host all of the files and recordings. So we will make sure to send that information out when that's finalized. But if you need access today, you should also have yesterday's meeting, and the recording should be the last object in the chat line of the Teams meeting. So good question. Thanks for asking that. So with phases, remember that phases work in the standard optimal control problem formulation, where it is minimize your objective subject to equality constraints. So you're driving your equality constraints to 0, and inequality constraints, which must be less than or equal to 0. So just remember that that's the standard formulation of an optimal control problem. So that is what Asset is always expecting when we formulate our problems. So transcription methods, I know we also hit on this. Essentially, transcription is you have continuous dynamics in your ODE that you wrote. You have the continuous mathematical definition of the two-body problem or the CR3BP, but you need a way for a numerical solver and optimizer, you need a way to transcribe that continuous problem into a numerical formulation. That's what our transcription modes do. It's a way of mapping the dynamics, equality constraints that are required to be satisfied for your phase to return an optimal solution. If you can't meet the dynamics of your problem, then you obviously haven't optimized the problem you're trying to solve. Transcription is how Asset under the hood can handle that. So Asset comes with 2 different transcription types. Co-location is the one that we suggest using. It's more robust, and most problems you can use co-location for. So Legendre-Gauss-Lobato co-location, we have 3rd, 5th, and 7th. So when you put in your transcription mode, it's a string of LGL 3, 5, or 7, depending on what order of polynomial fit you need. And of course, co-location is a well understood and well known transcription method with lots of extensive publications and documentation on that if you want to know more. But if you are also working in something that needs to be air controlled, tighter air controlled, or has fast dynamics, you can use a central shooting scheme for transcription as well, where you're taking your segments and between your segments, you are integrating forward and backward and have an error controlled difference that your ODE integration must meet. So these are just the 2 ways to form a phase and tell the phase. You know the ODE equations. Here's how I want you to set the ODE to be represented and held in this problem. So here's just another quick example. Again, I know this is a rehash on instantiating a phase. So you're probably very comfortable at this point that we define a structure in Asset, and then we instantiate Asset objects from it. So we've got an instantiated, in this case, low thrust ODE object, and we can instantiate a phase where we pass it a string for transcription, we pass it an initial guess, so a list or array with time history of states. The Asset integrators that we went over yesterday is a great way to generate initial guesses for this traj, and then number of segments that you want to partition the problem into. We also then went over, there's the ability to add these static parameters. So set static param, you can pass in a list with however many static parameters you need for your problem. If you're using static params, I often find that if I'm using them, I only have one for a problem, but there's not a constraint on any arbitrary size of static parameters. And those are terms that are not part of your dynamics. So they're not evolving over time with your states. They are an external variable that the phase is allowed to change and manipulate subject to any constraints that are put on it to achieve optimality.
You have 250.
Yes.
It doesn't need to be 256.
It does not need to be
It doesn't need to be a
256.
power of 2.
Correct. Yes. The number is a good point. The number of segments in this example is arbitrary. The number of segments also does not have to be the same as the number of points of your initial guess. That you'll do a interpolated solution of the number of segments from your initial guess.
Can segments be done in parallel?
Segments done in parallel.
Right. So they don't evaluate segments in parallel at times.
So you can solve your segments multi-threaded.
Okay.
So we'll get to
They
that.
are
in
multi-threaded.
Optimize.
Doesn't need to be.
Yeah, all of the function evaluations by default are multi-threaded.
And they don't need to be a power of 2 though.
No, yeah, it's kind of just a habit that we set it as a power of 2 because we, in addition to parallelizing function evaluations, we vectorize them, and we vectorize them in packs of 4. So if you don't know how many segments you use, I always use something that's a multiple of 4. You don't have to do that; it'll work without it. But just if you're just trying to pick a number, a multiple of 4 is the most efficient.
That's where I was going.
Yep.
Perfect. Yes, no, arbitrary number of segments, but it does get vectorized. So I won't go in as detail here today as we did yesterday, but the next few slides talk about once you've got a phase instantiated, how do you add constraints and objectives to it? What's the syntax interface with it? And the first part of that are these phase region flags. So whenever you do phase add equality con, add inequal, or add state objective, the first input to that is a phase region. That is essentially saying what part of the trajectory that you're representing with this phase are you applying this constraint or objective to. So one phase region flag is first or front. Those are equivalent statements. That is applying the constraint just to the first point or first segment in this trajectory arc for your phase. So a great use case of the first or front flag as a phase region is for initial conditions, saying you are constrained, your problem is constrained to be at some initial condition evaluation. There's also back or last phase region flag. That one is used for terminal conditions, or you can use it if your objective function is just a function of your final state or final point. Then, of course, there's path constraints. So say you need your spacecraft to always stay within some keep out zone, or never let your Earth orbit come closer to the Earth than some minimum periapsis value. You can apply a constraint on path, and it will apply this constraint or objective to every segment and point in this trajectory being represented by phase. And then one last one that's a little bit more esoteric, but it does get uses certainly, is front and back. So you can pass in, you don't care about the intermediate points for this constraint or objective, but you're passing in states from the first and the last component. One important reminder with that, for this methodology or syntax of doing add equal con, where you're passing in a vector function that is being constrained, when you do the front and back transcription method, recall whatever states you set. So say you do, the three position components and 3 control variable components. This function is actually going to be sized 2 times however many states you're passing in, because it's going to pull the states from the front and from the back. So if we do, the vvars is the 3 position and the 3 control scalar sections, we're actually going to get a size 12 function because it needs 6 from front and 6 from back. So again, we're back to in the very first set of slides, know the size of your vector function arguments that you need to pass into your functions. So here's just examples real quick of actual syntax examples of adding equality cons, inequality cons, and state objectives to these different phase region flags. You've got some vector function evaluation you're passing in, and then you can pass from the vvars, which are your states, time, and control, as you can kind of see from this notation down here. Or if you have ODE params, that is a second set of input, the second list of inputs you can pass. Or if you have static parameters, that's the third list of inputs you can pass. So these are all ways to interface and bundle what data is getting passed into the vector function argument of the appropriate size. So here's examples of that as well. Add equalcon front. If you don't need ODE params, which I know I mentioned, there are very rare cases that you have an ODE param, so often this is empty. If you don't need ODE params and you don't need static parameters, you can also use these function calls and just pass in the states, time, control list. You don't need to always append the two empty lists at the end if you're not using them. So that's just.
And we should add, Aaron, in most cases, this is going to be the interface you use, because these other parameters are not going to exist for most problems you're dealing with. So really, you just need to remember this, add equalcon, phase region, the function, and the variables it takes. And the shorthand version is what you're going to be using most of the time.
Great point. Yeah, very true. There's additionally examples here of two different phase regions we haven't covered just yet, of the phase region of your ODE params and the phase region of your static parameters. So you can append equality, inequality constraints to the parameters that you're using as well. So you can constrain those to match what's appropriate for your problem if you're using them. So on top of that syntax of phase add equal or add inequalcon, you can add integral objectives where you're passing in a function that you want to integrate and add your objective function. You're trying to minimize the total accumulated integration of this function evaluation subject to whatever this function is, and you're passing in parameters. And once again, if you don't have ODE params or static parameters, you can just do the function and the vvars, your position or states, time, control. There is a special type of equality constraint you can add, called adding a boundary value. So on the back end, this is an equivalent statement of adding an equality constraint, really, but it's if you need to bound a certain phase region, you can use the add boundary value. So this is a good shorthand. For example, if you have a set of initial conditions that you must constrain your problem to, you can just say add boundary value to the first or front phase region, have which v variables, the states, time, or u that you need, and then the values that you actually want them to be set to. So here you don't have to have a vector function that you instantiate and pass in here. You can just use what indices of your ODE do you want and what values do you want those to be equal to. You can also add a boundary value to your static param phase region flags, for example. If you need your first static parameter to always be equal to 1.0, you can, of course, add a boundary value condition to that. There's also upper and lower bounds that you can set. So a special type of inequality constraints where, again, you're picking the phase region flag. You're going to pass in the state variable that you're using, so states, time, or u. And then you can append a lower bound or an upper bound. So say you need your X position to always be between some region. You can even just do add LU var bound for the entire path, let's say, of the variable index that you want, and add its lower and upper bounds. If you have a function evaluation that you want to bound, there's functionality for that as well. So that's the upper or lower func bound. So that's a way to have a vector function that gets evaluated, passing in, of course, the appropriate variables that you need to hand as vector function arguments to that function, and then you can apply lower and upper bounds to that. So, for example, you could derive a vector function that computes maybe Keplerian elements from your Cartesian states and apply lower and upper bounds to things like that. And finally, there's the ability to add a lower and upper normal bound. So you can have a sub array from your state's time control. And if you want to have lower and upper bounds on the magnitude of that subvector that you're pulling, you can use this for it. So a very common use case for this is, say, we want the entire path, the 3 components of our control. We don't want the magnitude of our control vector to go below 0 or above 1. You can use the LU norm bound to just constrain the indices of your 3 control components so that the normal of your control is bounded to be within a certain region. So finally, this is the last section we're going to do for just the recap of phases. Then we're going to get to move on to even more exciting stuff. There's once you've got a phase constructed, so a reminder from the text on the right, you've got a instantiated asset ODE. You've instantiated a phase as a function of that ODE, or as a method of that ODE, given a proper transcription type, an initial guess, and the number of segments that you're handing it. You then go through and transcribe your problem that you need, so you can apply what's the objective function you're trying to minimize and what are all the constraints that this problem is subject to. Once you've done that, you can either solve the phase or optimize the phase. So optimize the phase, it's going to hand all of your operators that you've constructed to sciopt, our optimizer, and it's going to try to minimize your objective function subject to the constraints that you applied. You can also solve the phase if you need, so it's not going to optimize, it's not going to pay any attention to your objective function, so it's not trying to minimize objective, but it is trying to satisfy all of your constraints. So it gets you a feasible solution, not necessarily an optimal solution. And then there's other flags that you can use, like solve optimize, which will first run the solver and get you into a feasible solution. And then your asset phase will use that feasible solution from solve to run the optimize and then try to minimize your objective function and satisfy constraints. There's also a solve optimize solve. So it does that previous statement, but if your optimize call at the end fails, it'll rerun solve to at least get you back into a feasible space. And then there's optimize solve. So if you want to try to run the optimizer right away, say you trust your initial guess, you know it's your initial guess is in the close to what you would expect it to be, you can attempt to optimize right away instead of having to solve. But if that optimize call fails, it can resolve the problem to get you at least to a feasible space. So then another reminder is, once you've done one of these operations, you've solved your problem or optimized your problem, once you've done that, recall the initial guess you passed in, it does not get changed. This is still whatever same data storage as what you passed in. The values of your new solved or optimized solution are stored within phase. So we need a way of retrieving that data from phase. So you use the phase.return traj, and it will return you the segments that have been optimized or solved into a new list of time history of your trajectory. So once you run optimize, if you want your solution out, you need to get a data storage that can expect the return traj to now have a list of your time histories. So one thing we had a comment in the room that we wanted to mention here is by default, asset runs in multi-threaded for solving and optimizing. So under the hood, your problem is being vectorized and handed off in a multi-threaded manner. So there are times where if you have a well-conditioned, well-defined problem, and it returns an optimized solution. So it has minimized your objective function subject to your constraints within the tolerances that you have set. If it's a well-conditioned problem, you should get very close to the same answer every time. But it is important to mention that because this is run in parallel, if you are not set to run this in single-threaded, you could get slightly different answers between runs because it's handing those vectorized packets off to your CPU at different times. So don't be alarmed if you see optimized results that have minimized your gradient relative to your KKT tolerances, but have slightly different results between that. It will be within your tolerancing, of course, but we're doing multi-threaded operations in a numerical model. So just know that those packets could be getting solved at slightly different times. So there is a reason for that.
What is the mechanism that causes the timing to be different? I guess if you have the exact same, is it that you might have different CPUs doing different tasks at different times, and then therefore it would.
Yeah, it's numbers getting added together in a different order, basically, like round off error from whenever you're adding numbers of different scales and different orders, you can get different answers. It actually it's not necessarily the function evaluations. The nonlinear optimizer has to use a sparse linear solver to like factorize the KKT matrix at every iteration. It does that in parallel, and that is where most of the sensitivity to round off error comes, because factorizing a matrix, there's a large condition number to that. So small changes in us adding up numbers and them factorizing the parts of the matrix in a different order can lead to different solutions, and those can kind of compound. And they should be small, but they can cause slightly different numbers of iterations from run to run, and slightly different answers. But we're talking like Aaron said, it's assuming your problem's well posed and you're getting the same, falling into the same optimal solution every time. These are going to be differences in digits smaller than your tolerances. So it's not anything to be worried about. And if it is something you're worried about, set the thing to run single threaded. Like if you do need something that is 100% repeatable, set it to single threaded and it will be repeatable. But yeah, it's inescapable whenever you're using a multi-threaded linear solver inside of an optimizer. You see this in like iPopt as well.
I was just curious about I get the reason is because it could be a different order, but why is the order different from your computer?
It's literally your
and
computer.
If your antivirus kicks in and takes two of those threads, those are slow.
Yeah, it's on the order which threads are available on your overall system at that time. So the factorization is happening in parallel. So the threads that get handed off in your pool.
And the difference is probably true for different operating systems too, because Linux handles it differently than what Windows will.
Yeah, that's true. Yeah, whichever threads are your machine, which is of course subject to your operating system, what's currently running.
And as an example, Stu said under this problem, what I thought about. If you say, so like my Linux machine has 32 threads, right? If I kick that down to 20 or like 50, sure. If I kick that down to 20 or 15, then it gives a lot of the other issues, like with the other stuff that's running in the background, other threads to run. And so then this becomes a non-issue, because then those subset of 20 threads hit about the same time. That's not a problem.
Yeah. So that is it's a natural it's a natural phenomena for any solver that's running with parallel thread evaluations. It can be
Other
controlled.
thing to keep in mind is a lot of times we see people where the problem's really tough, and you can that variance for multi-threading people get disturbed whenever this happens. The variance for multi-threading can change you from convergence to non-convergence. That's usually just a signal that this problem is really hard, very sensitive. But once again, if you're in that case and you're thinking like, is there a bug in this thing? Like, is this thing actually like bugging out? Because I don't like that it's getting, converging one and then run it again and it's not converging. Set it to single threaded and you'll see that it will get you the same answer every time. It's just that there is that multi-threaded variance that can come in. There's not really a great way around it other than and no one of those answers is any more right than the other. It's just these condition number on some of these harder problems can be very high, and you can, when you're multi-threading, one run will say I'm converged, and another run will say I didn't converge. Just set it to single threaded if you're concerned about that. But that can happen, especially on like really ill conditioned problems. I know we've all seen that before, but that is not a bug. That is just how it works. It's unfortunate, but that is the reality of using a multi-threaded optimization scheme.
I guess one of them, since I ran into that very problem. So when I switched to a single threaded, it's like abysmally slow because it's single threaded. And so given that we understand what the problem is and why, what I'd actually write, because now you have this nice Python interface that you can do whatever you want, right? And so I'd run with the default number of threads and all that stuff. And then if I were to run into a problem where the solution would not converge, I kind of put it into like a for loop and said, cool, knock down the number of threads to something smaller. So it still takes, it takes a little bit longer to run, but not as long as a single thread, and see if I actually get an answer. Then when I get that answer, then go back and look at it to make sure it's okay. Kind of flag it saying this was kind of a problem child.
I mean, the only thing I would say to that is, I mean, that would have to be a really sensitive, because I mean, in general, it should just converge. This kind of this happens on problems that are so marginal, like doing a really fast flyby of something where like if it takes one small step, it like ends up trying to fly through like the moon or something, and then your transcription just can't handle that. That's typically where you see this type of thing. And Ben, right. I think that was basically the problem that you saw this on, wasn't it?
Yeah, I was trying to actually hit the earth. So
yeah, so that's exactly where you would expect this to happen. It's just
when you get deep in a gravity well, things get kind of sketchy, especially when you have to propagate it like 10 years out, and
and that's where you think like if you had like a change of like 1 e to the -6 and like a velocity coming in from iteration to iteration, that's the difference between hitting the moon or not, and that's where you see those. There's where you might see it. Oh, this run didn't converge and this one didn't. So typically, and that's a good. Whenever you see that kind of variance out of the optimizer, that's a signal that your problem is very sensitive. You may want to start thinking about how do I put more constraints on this to keep it from doing that. I mean, it's typically a good signal that hey, I need to put some more constraints on this to keep it from doing things like that, because you can always constrain it to make it behave better.
Yeah, and we should mention too, this is a fairly technical and slightly esoteric use case that we're covering here. So don't fear or think that that assets like a stochastic tool.
So, you only see this on really hard, very sensitive problems, and you would see this with any other tool as well. Yeah,
this is not a asset is bugged or any problem you try and solve, you're going to get some stochastic approach. This is essentially, we're really just trying to address here, if this is behavior you're seeing, to me, that is a flag to myself. If I have a problem that on one run in multi-threaded is converged and the other it doesn't solve, the first instinct to me is, okay, I'm likely not constraining and transcribing this problem properly. So you go through the debug and talk yourself through again how this is a highly sensitive problem. And by highly sensitive, like we said, we're talking you're flying in after 10 years of propagation to hit the Earth. This is not highly sensitive in the terms of you're going to a Lagrange point orbit. It's much more sensitive problems than that. You can get this kind of behavior. And in that case, now it's take time as a user to evaluate, am I transcribing this problem in a stable solution space? Am I forming a stable subspace that we're trying to solve?
So it's a quick question for on that kind of on that line of thought is, if you get to a point where you think you don't have the right collocation pattern, things like that, I mean, is there like a way to distribute the nodes between the two boundary points? And then is that automated, or is that something that you have to attend to or nurse the problem once you see the results?
No, so we don't cover it in this training just for the sake of time, because it's kind of a fairly simple addition on top of what we're talking about here. There's a completely automated mesh refinement algorithm. It's covered in the tutorials on the documentation. You'll need to know everything we talk about today everything we talk about today is a prerequisite to that. But yes, there is an algorithm, completely closed loop automated, where you'll have to give it an initial number of segments up here, but you'll also give it a tolerance that you want for like your integration accuracy, and then it will figure out the right number of segments and the placement for those, all automated, and it'll basically loop through and try to resolve the problem until it meets that. So yes,
okay, so you can add segments automatically and distribute them automatically.
Yes, it will do all of that for you. There's a section in the documentation. Let me see. It's
the last section in the tutorials on documentation with the header.
Adaptive mesh refinement. We give a little bit of overview of how it works, and then show the API for how you set these settings on the phase to control all of this. It's turned off by default, but it's just a single flag to turn it on, and it will do all the segment distribution automatically.
Additionally, also, if you don't need mesh refinement, but you suspect that over the course of a phase you've got one region that you want denser segments, there is a way to, instead of linearly space your segments, there is a way to pass in a list of regions of your phase and how many segments you want in that specific region.
Yeah, a lot of times, like if you're like starting at periaps of some highly eccentric orbit, you can say, I want to pack more in my initial guess. I want to pack more states here, and then I need less out towards the end, and that helps the initial like optimization figure the problem out, and then the mesh refiner can figure out the rest. That is also covered in the tutorial. We're just kind of cutting that out for time here.
Yeah. So does the mesh refinement have a preference for maintaining the number of nodes or segments over the distribution?
It's going to try to use the exact right number of segments to meet the tolerances. So it can actually, if you've used a lot of times you'll see this because we're always pretty conservative with the number that we use on the initial mesh. So we may use 500 evenly distributed, but there's a significant variation in the sensitivity of the dynamics. So it will actually reduce the total number of segments, but pack more in certain spaces of the trajectory. But it's always trying to use kind of the exact right number to meet your tolerances. And we use like error density functions to do all of that. It works pretty well. But yeah, it can increase the number of segments if that's what it needs, or it can also decrease them and just shift their locations to try to be kind of efficient with its. The fewer number of the segments, the more efficient everything is. So it tries to balance both of those.
Okay, that's cool. Thank you.
As a user of this, when shipping that for business, same issue. It is pretty impressive, and it works really well because it solved my problem too, just with the parallelization. So.
But yeah, that's covered in the docs. But I think once you see all of this, it'll be very easy to see how all of that fits in. It's an additive on top of this. It's not something completely separate.
Yeah, and this is just one more example why each of these slides ends saying make sure to go to the documentation, especially these phase objects and what we're going to get into next with the optimal control methodologies and objects. It's very extensive. So this training is trying to get everyone up and running with them where you can solve problems, but there's a lot of utilities and convenience functions built in as methods of these that the documentation covers in more depth than we're just able to do in a training. So with that kind of recap of phases, I don't want to spend too much time rehashing what we've already gone through. I just wanted to go through this section, these first 19 slides of this section, to really bring back to your memory, because it was at the end of the day yesterday, and I know it's the morning now, how these phases work. And we did go through an example yesterday on constructing a few different problems with these phases and solving them. So here is where we're going to take just a quick break and move on to the next section, which is optimal control problems, where we're going to start stacking phases together to form more complex and, if we need, multi-objective problems. So that's why we wanted to rehash these phases, as these are the key interface that you're going to use for solving complex problems. One thing, I don't think it came up as a question yesterday or this morning, but one thing when James and I were prepping for this is James brought up the good point. Anytime you're looking at solving a problem with phases, if you have, oh, where's my mouse? Yeah, if you find that you want to apply a constraint or something to one of these intermediate points, that is a good signal to you as a user that you should actually have multiple phases and patch those phases together at that point. So if you have a periapsis pass that you're trying to do some constraint to or add your objective function to, and it's actually in the middle of a phase, that's an index to, or a reminder to yourself here of, okay, let's do one phase that goes to that point of interest where now we have the back phase region flag. And then let's have another phase that adds on after that and patch those together. So we're going to take just a 5-minute break and we'll pick back up at, we're going to take a 10-minute break and pick up at 9:20 and go over optimal control problems, which is how we take multiple asset phases and patch them together into one problem that we're trying to solve.
Aaron, one thing I did remember, somebody at the end of yesterday asked about the bang bang control profile at the end of these slides. Can you go to that?
Yes. Yeah.
Yeah, I just wanted to add to that, that whoever that was, you are correct that there is some slope there. And the reason for that is we're using a finite discretization of this problem. Is if we were to use more nodes to approximate the problem, that would slowly go into the exact bang bang profile where it immediately shuts the engine off. But just because we're using, I think in this case we're using like 128 segments, it's trying to approximate this shape here with 128 straight lines. So some of them might be sloped, even though it is trying to go, because it's trying to go between 0 and 1, and those intervals at the switches are finite. So it is a sloped line going down. But if you use more segments for this problem, that is slowly going to begin to approximate that exact bang bang profile. So that's just a
that was me. So
yeah.
so these although they have some slope, there's a the discretization presents a slope to it, even though we know it's a discontinuity in the control.
Right. Yeah. It's just trying to use polynomials to approximate something that's discontinuous. So at those discontinuous points, there's going to be some residual slope because it can't just turn off immediately. That's kind of the drawback of using a direct method. I mean, you're never going to get exactly the switch points unless you were to use multiple phases at the different switches, and then yes, you can get exact on and off behavior. But I mean, that's just not a side effect, but that is just a consequence of using a direct method to try to discretize the problem rather than an indirect method where those switches are going to be factored into the dynamics. You may have like a smoothing law on them, but you can get, if you're using an indirect method, you can get those exact switches. But you could take the solution from this and then pass it off to an indirect method to really get the exact switching times if you wanted.
Yeah. So would it be possible to, if you kind of got a hint at how many bangs you're going to have, you could probably retranscribe the problem to based on the number of phases and have those be boundary points?
Yep. Yeah, you could definitely do that.
Copy.
And then another thing you can do, it's not covered in this tutorial. You can pull the co-states associated with any problem. And so if you had like an equivalent indirect method, you can pull the co-states, and they're really good initial guesses for those. So the indirect method will probably solve very quickly and get you the bang bang profile you're looking for. So that's another option if you have an equivalent indirect model, because the indirect models typically they don't have a great convergence radius, so and direct methods do. So you can, and one option is to use the direct method, pull the co-states out of asset, and give it to your indirect method, and then it should clean it up very nicely.
Perfect. Good reminder. So I think at that, I think we're ready to move on to phases. So we'll take a 10-minute break and pick up at 9:25 now.